Good afternoon. Lesson 1-3, video number 2. Okay, so limits of trig functions. Treat a trig function just like you did all your homework the other night. Start every limit problem with a direct substitution. So substituting 1 for x, I get the secant of pi. Pi is the reciprocal of the cosine function. Cosine of pi is -1, so my limit is -1. Direct substitution, tan of pi over 2. Pi over 2 is up here on the unit circle. It's the point 0, 1. Sine divided by cosine. Direct substitution would give me 1 over 0, so the limit does not exist. Cotan of -3 pi over 4. -3 pi over 4 is in my third quadrant, so the tangent and cotangent are positive. Reference angle of pi over 4, so +1. Direct substitution, sine of 0 over 0. Sine of 0 is 0. So now we have one of our indeterminate forms. Okay, so an indeterminate form with a trig function. It's not as simple as factoring or rationalizing. They use their own trig limits in order to evaluate the problem. Okay, know these really well. That's my code for you have to memorize these, and I hate to say that, but if you memorize them, then you won't have to prove them every time you're asked to use them. So take a minute and pause the slide so that you get both of them. Limit as x approaches 0 of sine of x over x is equal to 1. Limit as x approaches 0 of 1 minus cosine x over x is equal to 0. So let's use them. Limit as x approaches 0 of the sine of 2x divided by 2x. So this theorem, the sine x over x, these have to be the exact same in order for the theorem, for the limit rather, to equal 1. So since I have the sine of 2x all divided by 2x, I can just simply apply the theorem and the limit is 1. If I have a problem like this, sine of 3x divided by x, I can't manipulate anything that's attached to a trig function. So in order to use the theorem, I need a 3 in the denominator as well. Well, we can do that. We can introduce a 3. Really, we're multiplying by 1/3 so that I can get that 3 in the denominator. But if I'm going to divide by 3, then to balance the expression, I need to multiply by 3 over 1. So maintaining the original expression, because we really just multiplied by a form of 1. So now these two expressions are equivalent. The theorem directly applies. Oh, hold on. So this limit, using the properties, 3 on the outside times the limit, which is 1, so the final answer would be 3. Still start every problem with a direct substitution. So for our next one, limit as x approaches 0 of tan x over x. Direct substitution, tan of 0 is 0 divided by 0. Now, this function doesn't fit one of the special trig limits yet, but we always have to think outside the box with trig. I can rewrite tangent as sine divided by cosine. Dividing by x, I can write that as times 1 over x. Now I'm going to manipulate the expression even further. I'm going to put the sine x over x because I know something about that limit, and then I'm going to multiply that by 1 over cosine of x. Now using the limit properties, which I will give you a copy of to have, I can take the limit of the first term, product rather, and multiply it by the limit of the second product. This is the theorem. Limit of x as x approaches 0 of sine x over x is 1. Using direct substitution on the second, cosine of 0 is 1, so my final answer would be 1. Limit as a approaches 0, sine of a all over negative 2a. Okay, so the theorem requires that, oh, we don't want a black highlighter. The theorem requires that whatever follows the trig function has to be the exact same in the denominator. So the theorem works here. I have sine of a over a. What are we going to do, however, with that negative 2 in the denominator? The negative 2 is not affected by the limit statement. So I'm going to bring that negative 1/2 out front and multiply it by the limit of the sine function. If the 2 were with the sine function, we wouldn't be able to bring that to the front of the expression because the sine function is attached to that value. Because it's just a scalar value in the denominator, I can bring it out front. So I have negative 1/2 times 1, so my final answer would be negative 1/2. Limit as x approaches 0, x plus sine x, all divided by x. Direct substitution, 0 plus 0 over 0. Okay, now we have a plus sign here. So algebraically, what can we do? We can separate the numerator into two fractions. As long as I maintain the common denominator. Next thing I'm going to do, I'm going to take the limit of each term. X divided by x is 1, plus the limit as x approaches 0 of sine x over x. My first limit evaluates to 1. My second limit also evaluates to 1, so the sum of those two limits gives me a final answer of 2. And we will practice more of these in class. All right, take a minute, write down the conditions for the squeeze theorem.